Hi, everyone. My name is Soham Ghosh. I am a postdoc at NERSC, and I'm here to talk about performance portability in materials simulations. This work was done together with Victor Yu, a postdoc at ANL, Marco Govoni at ANL, and Brandon Cook here at NERSC. I hope that by the time my talk is done, you would have a good understanding of what a state-of-the-art material simulation can do, what applications you can put it through, and what results it can give you in real-life situations. And also what challenges you face when you take such a code and try to port it in a device-based cluster like we have here at the lab. Now, what do I mean by a classic material simulations? Essentially, I mean that there is no machine learning in it, and it is not done on a quantum computer. Well, so I thought I would start with an overview of material simulations. Now, usually, the starting point of many material simulations is DFT, density functional theory. It is a very attractive and quite useful method. It's so much so that I would say more than half of all material simulations has DFT as a starting point. Now, DFT is very useful and very fast, particularly because it takes all the complications of a many-body electronic systems with the many states possible in it, and encodes all of them into a single scalar function, namely the ground state electronic density. And for something that simple, the results that it can give is remarkable. However, it has many shortcomings, the chief among which is that it is a ground state system. It cannot give you any excitations. It cannot give you any anything that happens beyond any ground states. And it is quite bad at correlations. Those correlations are put into DFT using many approximations, namely LDA or GGA, and none of them are quite good when it comes to strong correlations. So what people usually do is use DFT as a starting point and then put different types of correlations on top of it. So you can use Hartree-Fock, you can use Monte Carlo, or you can use GW, which is perhaps the most complete and also the most complicated method, that classical method that you can use on top of DFT. Well, so then the question is, what can material simulations do? So what I will show in subsequent slides is a few examples of the practical examples of material simulations, starting from something pretty simple and ending in something that's not so simple. And once you have an idea of the applications, I will talk about the computational challenges that come with porting a code onto a device. And thereby comes the question of what programming models to choose and what performance you get based on such a choice, depending on what scenario you have. Well, so here are some examples of what material simulations can do for you. I have selected a few of them, starting from the simplest one and then ending in the not so simple one. So most people, as a starting point of DFT, calculate bulk bands and density of states. The example here is a bands and density of states of hydrogen 3 sulfide. And DFT is remarkably good and remarkably fast at giving you these results. It can calculate interfaces. The example here is an STEM image of a ruthenium atom and a ruthenium oxide interface. So the shiny part is the metal, and the not so shiny part is the oxide. And there is an inset that shows you the details of the interface in a blown up view. Well, What else can you do? You can calculate structural stability with phonons. The example here is a lanthanum hydrogen-10, a high temperature superconductor. The calculation is of the structural stability of using phonon calculations. So immediately without any experimental input whatsoever, you can get an idea of where at what pressure material is structurally stable, and then you can tell your experimentalist friend to go look for it under such conditions. Well, you can also calculate electron-phonon interactions and how it looks like in a momentum dispersed state. So the results are the interacting electron-phonon bands put on top of the single particle black lines. So the single particles are the non-interacting bands, which are Dirac delta functions. They have zero width. And the smeared thing on top of it is the effect of the electron-phonon interactions. And in the inset, I show you the impact of the interaction as far as the strength goes. So it bends the slope of the electron bands, and the bending gives you a measure of the strength of the interaction. And from the strength of the interaction, you can calculate phases. So the figure here is a stability instability phase of various high temperature superconductors, some of them almost room temperature superconductors under high pressure. And you can get a phase boundary of using absolutely no experimental inputs, purely ab initio methods. And I also have a calculation, an ab initio calculation of conductivity, in this case, Drude conductivity on hydrogen-3 sulfides. So these are all methods that start with DFT and built on top of it. So these methods in particular use something called EPW, electron phonon with 1 year, which is a complicated method, but not as complicated as GW. So none of these panels have any GW results. The GW results come in the next slide using specifically a code called WEST. So WEST stands for without empty states. And this is important because one of the major challenges of using GW is to account for the many empty states that you have to sum over. It makes your calculations more and more complicated as your number of empty states increase. Well, so WEST has a method of giving you the same results without considering any empty states whatsoever, only the valence states. And it can calculate self-energy and Green's function, the two most important quantities in any material simulation calculations. And it does so at a scope that's far beyond basic density functional theory. Because it can do so, it can simulate real solids, liquids, nanostructures. It can simulate photovoltaics. You can give you properties of catalysis. It can give you the results of real electron excitations, optoelectronics. It can actually tell you what happens when a photon hits a solar cell. It can tell you what happens, how much energy you can store in a system depending on what system you use, what interface you use, how much pressure you have. It's a code that's deployed on a large scale. It's massively parallel and it's GPU enabled. Well, the semantics, the flowchart of the code is given here. And along with the result on a fairly complicated interface, a COOH silicon interface. The flowchart is fairly complicated. I will go over it quickly. It starts with a simple DFT. You take plane waves, you make superpositions out of them, and you do a cone sham analysis of it. You get single particle electron states. Then you put them through a PDEP method. It's a method of calculating the dielectric matrix. So therefore, you calculate linear response on it. And then you do a Langshaw's method on it to get G and W, the two components of GW. The G stands for Green's function and the W stands for interactions. So together they make up the GW. And then from G and W, you can calculate the self-energy, sigma. And from self-energy comes quasi-particle energies. Quasi-particle energies here means the interacting analog of single particle energies. It tells you what the electronic states and absorptions energies and excitation energies of an interacting system is. The result on the right is the local density of states of a fairly complicated interface done with West GW. And it's remarkable what it can produce for a system that's fairly large and fairly real. Well, okay, so now how do you take a code like this and deploy it on a device? What are the challenges? What are the pitfalls? And what options do you have? Well, the options are fairly straightforward. You have an option between various models and various architecture. So models come in two broad categories. One is a directive-based model. OpenACC is an example. Kernel loop directives is an example. Both of them take a standard single thread code and put garnished directives on top of it. An example here is this double loop I show, which has a double summation loop with OpenACC directives on it. You can also use something like, say, CUDA BLAS, QBLAS, which is the NVIDIA GPU analog of BLAS. It does basic linear algebra routines for you. Or if you so choose, now you have the option of using standard Fortran directly on a device. An example is the last line of code. It's a single line that does the same thing that the top 10 lines in OpenACC does. It's remarkably simple when you can get away with it. So that's as far as the model choice goes. Now you have a choice of architecture as well. So on Cori, in the lab, you could use Intel Haswell CPUs, you could use V100s, you could use A100s. So here I have an example of A100s, and you can see how different that is compared to a CPU. And because how different it is, your programming philosophy and model should also reflect that. So right there, you see the number of choices you have, and the more choices you have, the more you have to think of how you refactor your codes for a GPU and how you port various parts of it. Now, I guess one question you can ask from this is, why can't I just pick the model that I am most familiar with? And I don't have anything to do with the architecture, because I'm given the architecture already. I either have a V100 or I have something else. So why don't I take the directive, that the model that I'm most familiar with, and deploy it on that architecture? Well, there is a problem to that. The problem I can show in this slide. What this slide does is take 4 different code blocks from a West routine and compare the performance in terms of the time it takes to run of a QBLAS and OpenACC, contrasting them together. It does it for 2 different systems. One is Benzene, which is a small system with only 15 electronic bands, and the other is Silicon. It's a silicon supercell, so it has 128 bands, an order of magnitude more than Benzene. And you can see how the choice of your programming model depends, the performance of your programming model depends on your system size. So for a small system, the QBLAS is better in all cases, in all 4 of the code blocks that I've chosen. Whereas in a larger system like Silicon, OpenACC is vastly better in many of the code blocks. So therefore, if you want good performance, you have to decide quite in detail about what programming model you want to use for what type of code blocks and what type of routines. Well, so here is the take-home message that you can also get if you look at the next few slides. So if you don't want to look at any more slides, you just want to know what what my suggestion is, the suggestion is in a single sentence that if you have nested loops with any sort of data dependence between them, you should use OpenSEC or something like OpenSEC, say OpenMP. Well, okay, so that's the one sentence take home message. To prove that, I'm going to take 3 different code blocks and deploy them on both CPUs and GPUs and look at different programming models and the performance on them. So the code blocks are fairly familiar. They're essentially matrix manipulations. The first of them is overlap, which is the formula is shown here. And the message that you get from these figures is do not use QBLAS, especially if your matrix size is anything large. So the figures show the performance in gigaflops. And on the x-axis is the matrix size, the column size of the matrix. So in physics terms, the column size is the same as the number of plane waves you have in your Hamiltonian, or in any other matrix, any linear response matrix, any dielectric matrix, whatever you want. So you can see straight away that OpenSEC and standard Fortran work very well. They're remarkably close to each other on a V100. And BLAS, it starts getting better and better as your system size increases, but it never catches up to OpenSEC. And the other lesson from this routine is that you should offload to a device as soon as you can, because the performance starts getting saturated rapidly on Haswell, whereas on a V100 or A100 it climbs up to an order of magnitude more than on Haswell. Well, so the quick reason why BLAS loses out to OpenSEC here is that with OpenSEC you can coalesce all the data movements and all the nested loops into one single kernel and send all of it at the same time onto the device. Whereas with BLAS, you have to send multiple kernels to the device, and that movement takes time, and that movement slows you down. Well, so that's as far as overlap goes. What happens when you look at something very familiar, AXP, AX plus Y? Well, there the results are that OpenSEC and CUF kernels are your best bets. I show the results for both A100s and V100s. The A100s are dots on a line, and the V100s are just lines. The A100s and V100s are remarkably close to each other. There's not much performance gains to be had. But OpenSEC and CUF kernels are miles better than, say, anything else, including BLAS. So for whatever you do for an XP, do not use standard Fortran. So the results here are on the top result is on V100s and A100s, and standard Fortran is really, really bad unless you are working with trivially small number of matrices, which you never will in a real system. If you have a large enough system, you know that your matrix size will always be huge. You can use BLAS, you can use OpenSEC, or you can use CUF kernels. They will all give you comparable results. But you have to offload to device as quickly as possible, because again, it will saturate your CPU very, very quickly, as you can see in the bottom left figure. Another thing that was interesting to me in this calculation is the saturation of the symmetric multiprocessors, in this case V100 SMs, for matrix size. So what I have plotted is the performance as a function of the number of rows of a matrix. So each line belongs to a matrix with a rows size that's double that of the next. And as you double the matrix size, your performance increases. However, it also saturates much faster. And I thought that was interesting that came out. So now I will come to the last code block, and the message will be familiar, but there will be a twist. So this code block is mixed precision GMV, A star times X. However, the problem, one subtlety here is that A is so large that you cannot fit a double precision version of it in a device. You'll have to, so I took a single precision version of it. And that results in something very strange. There is a performance increase all the way up to 2 to the power 14 columns. And then there is a sharp drop for both OpenACC and for cuff kernels. This is on V100s, but the same thing happens on A100s, but it does not happen on the CPU. I don't know why. You can, however, see that if you want to use something on the device, you should use OpenACC. It's still better than anything else. The platform dependence shows on this figure on the right, where strangely, if you have to use mixed precision GMV, you should perhaps just do it on the CPU itself. There is not that much performance gain going to GPUs, and certainly there is no performance gain when you go to large matrices. Well, with that, I'm going to conclude and reiterate my message. If you have multiple nested loops with data movement between them, you're doing any sort of summation, any sort of data dependence loops, you should use OpenACC. It's going to be more, it's going to give you better performance, and certainly it will be more portable. Whereas if you use something like cuff kernels or CUDA Fortran, then you're not going to get much performance benefits. You're going to get negative performance benefits compared to OpenACC, and it's not going to be portable onto anything beyond an NVIDIA system. With that, I conclude. Thank you for your patience, and I'll take questions if you have any.